Today's lesson is called Literal Equations Day 1. So let's start with a definition of what a literal equation is. Literal equations are equations with multiple variables. So to demonstrate this, we're going to solve each of the equations below for x. So I'd like you to take a second, pause the video, and I want you to solve the equation on the left. When you're done solving that equation, you can resume the video to check your answer. Okay, so this is a two-step equation. We want to undo addition or subtraction first always. So I see subtraction of 6, which means I need to add 6 to both sides of the equation. That gives me 2x equals 16. Now I don't want 2x, I want 1x. So 2 and x are being multiplied. The opposite or inverse operation would be to divide. So we're going to always divide by the coefficient, which in this case is 2. So then when we do that, we end up with x equals 8 as our final answer. Okay. Now let's look at the equation that's next to it. First, I want you to pay attention to the structure. Our original equation had 2x minus 6 equals 10. Our new equation has the same structure, ax minus b equals c. The difference is that there are no numbers involved in this equation. However, the process is still going to remain the same. We have to solve the equation for x. So when you see that, you want to think of x as your only variable. And everything else kind of acts the same way the numbers do. I need to get x all by itself. I need to move everything else to the other side. So I don't want the subtraction of b to be there. So just like I did in the first equation where we didn't want minus 6, so we added 6, we don't want subtracting b, so we're going to add b to both sides. So I get ax equals, now when I look at that c plus b, c and b are not like terms. I cannot combine them. So instead, I have to leave it as b plus c or c plus b, but remember, we typically write things alphabetically. Now I'm closer, but I need x to be all alone, and right now it's being multiplied by a. Just like in our original equation, our x was being multiplied by 2. So if I want to undo multiplication, I need to use division, and I'm going to divide by my coefficient of x, which is the letter a. That eliminates these a's, and I get x equals, now again, nothing I can combine over there, so my answer is b plus c over a. So I want you to take a second and complete a very fast quick write. I want you to pause the video and try these questions. You're going to identify the similarities and differences between the two equations. Please list them under the respective areas that you see there. Please pause the video, complete these two questions, and resume the video to go over the answers. Okay, at this time, you've had a chance to do the quick write. You were supposed to identify the similarities and differences between the two equations. So for similarities, both use opposite operations or inverse operations to isolate. So that's no different. If we see subtraction, we're doing addition. If we see division, we're using multiplication. The differences are that the literal equation does not simplify nicely because of the multiple variables. So you're only going to be able to simplify if you end up with combinations of like terms. If you don't, then your answer is going to stay looking more complicated than when we have numbers involved in regular linear equations. Okay, so let's work through some examples of literal equations and practice solving. For example 1, it says solve for w. So remember, my job is to isolate w. Our equation is P equals 2L plus 2W. So I'm going to rewrite the equation over here. And keep in mind that my goal is that the W is the variable and I'm trying to move everything else away from that. So I need those two L's that are on the same side as the two W's to move. That would be an addition or subtraction move, so we want to do that first. In order to get rid of a positive 2L, I need to subtract 2L. I still have to keep my equation in balance. So we know using our properties, if I'm going to do something to one side, I need to do the same thing to the other to keep it in balance. So if I subtract 2L from this side, I also need to subtract 2L from this side. Now, when we do this, the two L's are going to be eliminated. But on the left-hand side, I'm going to have P minus 2L because they are not like terms. I cannot combine them. They just have to stay like that. And on this side, I have 2W. Now, I don't want 2W. They want me to solve for W. That means 1W by itself. So right now, W is being multiplied by 2. We want to use the inverse operation, which is division, and we are going to divide by that coefficient that we do not want to be there anymore. Whatever I do to one side, I have to do to the other. So I'm going to cross out these 2's, and I end up with P minus 2L over 2 equals W. Now, looking at this, you might be saying, oh, wait, there's 2 there, there's a 2 there. Be careful. Warning, warning. You are not allowed to divide anything out or cancel things through unless all the pieces have a 2. So if there was a 2 in front of the P, we could reduce the entire fraction by 2's. But because there isn't, this is as simplified as it's going to get. You should not be dividing those numbers. You should be leaving your answer just like that. Okay, let's move on to example 2. For example 2, it says solve for M, which again means M is the one I need to be isolated and by itself. So I'm going to rewrite the problem. K equals 1/2 mv squared. And we're going to start making moves to get M all by itself. So the first thing I see there is a fraction that I don't want to be there anymore. So whenever we want to get rid of a fraction, we are going to multiply by the reciprocal. So I'm going to multiply by 2 over 1, the reciprocal of 1/2. Whatever I do to one side, I must do to the other. I'm doing that because now my 2 over 1 and my 1/2 will cancel. On the left-hand side, 2 over 1 is the same as 2, so 2 times k would be 2k. On the right-hand side, I still have m, v, and squared. Now I'm closer, but I'm still trying to get m alone, and I see a v squared over there with it that I'd like to get rid of. Because m and v squared are written right next to each other, I know that that is multiplication, so I have to do the opposite operation, which is division. I'm going to divide by v squared because that's what I'm trying to remove. Whatever I do to one side, I must do to the other. That allows these to cancel, and I end up with 2k over v squared because there's nothing I can do to simplify that. There's no like terms, and that's going to be equal to m. So I have successfully taken m and isolated it. Okay, let's take a look at example 3. Now solve the equation from example 2. So same equation, so I'm going to rewrite it. K equals 1/2 mv squared. We're going to solve the same equation, but now they want us to solve for v instead. So let's see how the steps change because I'm trying to now get v by itself. I want to start the same way because either way, I still don't want 1/2 there. So I'm still going to multiply by the reciprocal, which allows me to eliminate 1/2 from that side of the equation. And I end up with 2k equals mv squared. This is where the steps are going to change. I'm trying to isolate v now. So that means I don't want the m to be there. So I'm still going to be using division, but this time I'll be dividing by m to eliminate it from that side. So this will be eliminated, and I end up with 2k over m equals v squared. Now this is important. I don't want v squared. I need just v. So if you think back to when we were solving equations that involved x squared, once we had that x squared or whatever variable squared isolated, our very last step was to undo the squaring by taking the square root. So I'm going to take the square root of this side, which means I also have to take the square root of this side. So I end up with an answer of the square root of 2k over m is equal to v. So you can see how solving for v has changed the process for an equation that looks like that, and we ended up having to use square root. Now, our last example, number 4, is showing you a benefit of being able to take these literal equations and solve for a particular variable. It comes in extremely handy when we're working with formulas. So the formula for the area of a trapezoid is A equals 1/2 height times base 1 plus base 2. The first thing they'd like us to do on the left here in part A is to express B1. So that means this is what we're solving for. That's what we're isolating. And it says in terms of A, H, and B squared, or B2. Sorry, not B squared, B2. So what that means is we're going to have B1 all by itself. And the answer is going to have all of these other letters, A, H, and B2, as part of the answer. So that's what it means when it says express B1 in terms of A, H, and B2. Okay, so let's start with rewriting the formula. A equals 1/2 height times base 1 plus base 2. We do not want the 1/2 there, so I'm going to start similar to the way we did in example 2 and 3. I'm going to get rid of 1/2 by multiplying both sides by the reciprocal. When I do that, the 1/2 and the 2/1 are eliminated. So I end up with 2A equals height times B1 plus B2. So that's base 1 plus base 2. Now I'm getting closer, but I still have this H that I don't want there. And I know it looks like distributive property, but I don't want the H to stay, so I should not be distributing the H. I should be getting rid of it. Since H is written next to B1 plus B2 in parentheses, I know that that's multiplication. H is being multiplied by that. So I'm going to do the opposite thing, which is to divide, and I'm going to divide by H because that's the variable I do not want to be there anymore. So H's are eliminated, and I get 2A over H equals B1 plus B2. So very close now. I'm trying to get B1 by itself, which means I need to move B2. Right now it's being added to B1, so I'm going to do the opposite thing, which is to subtract it. Now over here, I can't combine 2A over H with subtracting B2, so they have to stay separate. So that's 2A over H, then subtracting B2. That is equal to B1. So now we know for sure that B1 equals 2A over H minus B2. So there's my transformed formula. Now, why does that help me? Because let's look at question B. The area of a trapezoid is 60. So A equals 60. The height is 6 feet. So it was 60 square feet. The height is 6 feet. And one base, so B2, we'll say, because we know we can find B1. So B2 is 12. We have to find the number of feet in the other base. So because I've transformed the formula already, I'm going to use that transformed one to find my answer. And because of that, look what happens when I do my substitutions. 2 times A, which was 60, over H, which was 6, and then minus B2, which was 12. That has allowed me to already have all the numbers on one side, and now I can just use my calculator, do the calculations, and have my answer, rather than using the original formula, having to plug in plus manipulate the formula at the same time in order to get my result. So here, I'm going to end up with B1 equals 120 divided by 6, and then minus 12. So this is B1 equals 20 minus 12, which means B1, or one of the bases, is 8 feet. So as a summary, the properties and reasoning used to solve equations apply regardless of how many variables appear in an equation or formula. So you're still using your inverse operations and your properties. Solving a literal equation allows you to solve for a specific variable in a formula, which is what we just did in example 4, which can be useful when solving applied problems. And that concludes your lesson on literal equations, day 1.